welcome to the deep dive. Today we're looking at some research that honestly sort of reframes what we thought generative AI could do. We're moving beyond just generating images.
Right. Into solving some seriously hard math problems, stuff that's been around for ages.
Exactly. We're diving into the paper, Visual Diffusion Models are Geometric Solvers.
And the core idea, the really surprising part, is that standard visual diffusion models think the kind of U-net backbone and stable diffusion can actually solve these classic, really tough geometric problems.
Purely in pixel space, right? That's the twist.
Purely in pixel space. It basically turns complex geometric reasoning into an image generation task.
And the problems they tackle are no joke. We're talking the Inscribed Square Problem, which is still unsolved.
Over a century old.
The NP-hard Steiner Tree Problem, and the NP-complete Maximum Area Polygon Problem, MAXAP.
And crucially, it's the same underlying architecture for all three. That's what points to something really fundamental here.
That universality, yeah. It feels like a paradigm shift, simplifying things compared to, the usual symbolic AI or graph-based approaches for these kinds of problems.
Definitely. Shows diffusion is more than just a creative tool.
Okay, so let's dig into this visual diffusion framework a bit more. We all know diffusion models making cool pictures. How do they suddenly become tools for, minimizing path lengths or finding squares and curves?
Well, it boils down to what diffusion models are really good at fundamentally. Modeling complex distributions, especially ones with multiple possible answers, multimodal distributions.
Right.
So people have used diffusion for optimization before, like for the traveling salesman problem.
Yeah, I've seen some papers on that.
But that usually involved working with, symbolic data or graphs. You needed specialized setups.
Which often means they don't generalize well if you change the problem size or specifics, right? They get brittle.
Exactly. This visual approach is different. It leans into the strengths diffusion models already have, with images handling situations where there isn't just one right answer, but maybe loads of them.
Like the Inscribed Square example you mentioned. One curve could have several possible squares.
Precisely. When you turn that into an image problem, the model learns to map noise to that whole space of possible valid squares. It handles the ambiguity naturally.
And the architecture is, almost basic, considering the difficulty of the problems.
Yeah.
A standard U-net with self-attention.
Pretty much. No fancy custom geometric modules bolted on. The cleverness is really in the data and the framing.
So how do they train it then?
They generate a huge data net of valid geometric solutions. Lots and lots of examples of correctly inscribed squares, optimal Steiner trees, maximum area polygons, and they just rasterize them into images.
Turn them into pixels.
Yep. Then they train the diffusion model to take Gaussian noise and, conditioned on an input image representing the problem, denoise it into one of these valid solution images.
Okay, let's walk through the first case study, because it really shows off that distribution modeling aspect. The Inscribed Square Problem, also called Toplitz's Square Peg Problem, posed in 1911.
That's the one. Still unsolved generally. The question is simple. Does every simple closed loop, a Jordan curve, have 4 points on it that form a square? Seems like it should, but proving it for any possible curve is incredibly tricky.
And like you said, a single curve might allow for multiple squares, so it's perfect for a generative approach.
Exactly. The method is pretty straightforward conceptually. Take the curve, draw it as a black line on a white background in a 128 by 128 pixel image. That's your input condition.
Okay.
Then the diffusion model generates an image predicting where the square should be. That's the $6 estimate.
128 by 128 pixels. That feels really low resolution for precise geometry. Isn't there an issue with, discretization error? A corner might look like it's on the line, but mathematically.
You've hit the nail on the head. Pixel space has limits. You lose that sub-pixel accuracy. So, yeah, the raw output from the diffusion model isn't quite proof level precise.
Which is where this snapping step comes in.
Exactly. It's a crucial post-processing step. They take the square the model predicted and apply a small adjustment, a tiny rotation and translation. It's a rigid transformation.
So they're not completely resolving it, just fine-tuning the model's answer.
Precisely. They optimize this transformation to maximize something called the alignment score. Basically, you want to minimize the average distance from the square's corners to the actual curve geometry. Closer to 0 is better.
And did it make a big difference?
Huge. The paper shows the numbers. Before snapping, the alignment score was Manicos 1.60 on average.
Meaning the corners were, on average, 1.6 pixels away from the curve.
Roughly, yeah. But after snapping, that improved dramatically to Manago 0.90.
Okay, so less than a pixel away on average. Much better.
Much better. And importantly, the squareness of the predicted shape, they measured that too, stayed really high, close to the ground truth.
So the diffusion model got the basic shape and location right.
Yes, it captured the overall structure and where the square should roughly be.
And the snapping just provided that last bit of geometric accuracy needed because of the pixel limitation.
That's it. Diffusion for the structure, snapping for the precision.
Okay, Inscribed Square shows how it handles ambiguity. What about just raw, hard optimization? That brings us to the Steiner Tree Problem, NP-hard. The kind where computation just explodes as you add points.
Right, the Euclidean Steiner Tree Problem, or EST. Connect a set of points, your terminals, with the shortest possible network. And you're allowed to add extra points, Steiner points, to shorten the total length.
Super important in the real world, right? Like network design, chip layout.
Absolutely. Fiber optics, printed circuit boards, telecommunications, every bit of length saved matters.
And the optimal solution has these really specific geometric rules, doesn't it? Steiner points have 3 connections, edges meet at 120 degrees.
Very tight constraints. So how does the visual model handle that?
Yeah.
Again, it's surprisingly simple. They just rasterize the entire solution, the terminal points, the Steiner points, the connecting edges into a grayscale image.
The whole thing.
The whole thing. Same UNet architecture, conditioned on just the terminal points this time. The model implicitly learns the 120-degree rule and the minimum length property because those are the only kinds of solutions it sees during training.
Okay, but then getting the solution back out of the image sounds tricky. They talk about finding blob centroids for nodes and then checking pixels along lines for edges. That sounds like it could easily mess up for an NP-hard problem.
It does sound a bit fragile, I agree, but I think it works because the diffusion model has learned such a strong prior about the visual appearance of an optimal Steiner tree. It knows the general topology, the structure.
So even if the recovery is a bit fuzzy, the underlying structure generated by the model is already very close to optimal.
That seems to be the case. It's learned a powerful visual heuristic that guides where things should be, so the simple recovery methods are good enough.
And the results back this up, particularly the generalization.
Oh, absolutely. Table 2 in the paper is pretty compelling. They trained it only on small problems, 10 to 20 points. And in that range, it's incredibly accurate. The length ratio compared to the true optimum is like 1.0008, basically perfect almost every time. 99.6% valid solutions.
Wow. But the really impressive bit is scaling up, right?
That's the kicker. They tested it on much larger instances, 41 to 50 points, way outside the training range.
Yeah.
The ratio only went up slightly to about 1.0092, still incredibly close to optimal. That kind of generalization is amazing for an NP-hard problem where traditional solvers often just fall over or take forever as the size increases.
So the visual approach seems to scale much more gracefully. It's like it learned a general visual pattern for shortest network that works even for bigger, unseen problems.
Yeah, it's effectively learned a very efficient general approximation algorithm just by looking at examples.
Okay, so we've seen ambiguity with the square, optimization with the tree. The third case, maximum area polygon, or MaxP, gives us this key insight about why diffusion, why the generative approach is better than maybe just simple regression, right?
Exactly. AXXApp is NP complete. Given a set of points, find the polygon that goes through all of them and encloses the maximum possible area.
Now, for many point sets, there's often just one unique polygon that does this.
Right, so the logical question is, if there's usually only one answer, why bother with a probabilistic generative model like diffusion? Why not just train a standard regression model, same UNet architecture, to directly predict the image of that single best polygon?
Seems simpler. No noise needed.
It does, and they tested exactly that. They ran an ablation study comparing the diffusion model against a regression model using the same network backbone.
And what happened with the regression approach?
It didn't work nearly as well. The key finding in their table 4 is that the regression model tended to output blurry or fragmented polygons. It tried to average the geometry, essentially.
Like trying to average slightly different drawings and ending up with a smudge?
Kind of, yeah. And that blurriness caused the recovery process figuring out the actual polygon vertices and edges from the image to fail massively.
How badly?
For point sets of 7 to 12 points, only about 36% of the predicted polygons could be successfully recovered as valid, simple polygons. The outputs were too messy, geometrically unsound.
Okay, so relying on one single, potentially slightly imperfect pixel output was too brittle.
Exactly. The discretization errors and slight imperfections meant the single deterministic output often wasn't a recoverable polygon.
But the diffusion model.
The diffusion model provides robustness because it's stochastic. You can run the sampling process, say, 10 times, each starting from different noise.
Get 10 slightly different potential solutions.
Right, 10 distinct, sharp candidate solutions. Then you just check which of those 10 candidates is a valid, simple polygon and gives the largest area.
And that worked better.
Much better. Using this strategy, Generate 10 picked the best valid one. They achieved a validity rate of over 95%.
Wow, big difference. So the takeaway isn't just that diffusion is better, it's that modeling the distribution of solutions, even if it's a very narrow distribution around one optimum, gives you resilience. Resilience against the noise and errors inherent in using pixels.
Precisely. The ability to generate multiple sharp samples makes it practical. It shows why the generative approach wins out over simple regression here, even when the problem seems deterministic.
Okay, so let's zoom out a bit. We've looked at these three very different, very hard geometric problems. Inscribed square, existence, ambiguity, Steiner tree optimization, NP hard, Nagus app, maximization, NP complete, uniqueness issues.
And the remarkable thing is they use the same core visual diffusion architecture for all of them. That points towards a really general framework.
It really does. And you mentioned looking at the denoising steps. There was something interesting there about how the solutions form over time.
Yeah, if you look at the visualizations in the paper, figures 3, 6, and 9, they show the model's prediction, the $6 estimate, at different time steps during the diffusion sampling.
Okay.
And you see this consistent pattern. Very early on, when there's still a lot of noise, the global structure of the solution appears. The rough placement of the square, the main branches of the Steiner tree, the overall shape of the polygon.
The big picture stuff first. Low frequency features, you could say.
Exactly. The model gets the course layout right almost immediately. Then, the later time steps, when the image is much cleaner, are spent refining the details, getting the edges sharp, placing the vertices precisely.
That sounds almost like how a person might approach it. Sketch the rough outline first, then go back and fill in the details carefully.
It's a really neat analogy. You establish the main structure, then you refine.
And that observation could have practical implications too, right? For making it faster.
Potentially, yeah. If the main structure is set early, maybe you don't need as many refinement steps later on. You could perhaps allocate more computational budget to those early steps, or just run fewer steps overall and still get a pretty good solution much faster.
Interesting. So it opens up avenues for optimizing the solver itself.
Definitely. But the bigger picture here, the main conclusion really, is that this generative muscle that we see in models making art or realistic photos, it's actually a powerful general-purpose tool.
It's a tool for what? Recognizing mathematical patterns.
For recognizing and synthesizing complex mathematical distributions, but doing it through this universal language of pixels, of visual space.
So the idea is maybe any problem you can represent visually with constraints. Even if the underlying math is super complex, maybe this approach could work.
That's the provocative thought, isn't it? It makes you wonder what other really complex problems, maybe in scheduling or resource allocation or graph theory problems we currently tackle with very specialized, brittle algorithms.
Yeah.
Could we potentially solve them more generally, more robustly, just by figuring out the right way to draw them and letting a visual diffusion model learn the patterns?
Shifting from making pictures of cats to solving century-old geometric conjectures with basically the same tech.
That's
it's a deep dive into where AI might be heading.